and we're going to be talking about section 3.6, and what we're talking about here is analyzing arguments, and we're going to be using truth tables to do that. So we're going to be talking about truth tables with two premises, valid and invalid argument forms, different ways of deciding whether an argument's valid, truth tables with more than two premises, and then we're going to look at some examples from Lewis and Carroll, like Alice in Wonderland, to figure out some information. So we used Euler diagrams on the last section, and that worked well when we had fairly simple problems, but when we have more complex problems, the Euler diagrams just won't work. They're too complicated. So what your options are here is to test the validity using a truth table. So what we're going to do first is assign a letter to represent each part of the argument. So we're going to pick a P, a Q, an R. It doesn't necessarily matter what order you label them in, as long as you are consistent as you go through it. Then we're going to express each premise symbolically with the implied symbolism or the and symbolism. And then we're going to put it all together into the form of a conjunction, with the antecedent and the consequent, and then we're going to go through and do a truth table. If the truth table is a tautology, meaning again that all of the arguments are true or valid, then it's a good valid argument. Otherwise, it would be invalid. So here we have an example. If the door is open, then I must close it. The next statement is the door is open. So the conclusion is I must close it. So this is a very simple example, and according to the rules, it is a valid argument, but we're going to prove it using this idea of the premises that we were just talking about. So the first thing we have to do is assign to the parts of this problem P's and Q's. So again, we're going to sort of stick logically with this and go in order. So we're going to call the first part of the problem our P. So this is going to be our P. So when they're talking about doors opening, is always going to be P. Closing the door will always be Q. So the next part here says the door is open. So we've already labeled that as P. And closing it, we've already labeled that as Q. So this is what we ended up with. P represents the door is open. Q represents that I have to close it. So because we have an if-then statement at the top, then we use that symbolically. We show that with the arrow. So we have P implies Q. The next statement just says the door is open. It's just a statement. It doesn't have an if-then part to it. So we just write the statement, which is P, and the door, or I must close it, is our Q value. So this is what we have. So basically what we are saying is that P implies Q, and P is true, implies that Q must be true. So we put that into a statement. We have the P implies Q, which was the first part of the sentence that said, if the door is open, then I must close it. And I have the part of the statement that says, the door is open, so that's my Q. If all of that is true, then Q, which we already decided earlier was, I must close it. So now what we want to do is find out whether this is a valid argument. We want to prove it, that it is a valid argument. So we're going to do our truth table. So we have two premises. So again, we're going to have P and Q. And our truth table is going to be set up with the true, false, true, 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 false, false, true, false, false. And we're going to fill in our truth table with all of our information. So P implies Q. So we're going back again to, I forget which section again. It's section 3. And our truth tables for this. So true and true is true. True and false is false. False and true is true. False and false is false. I'm sorry, false and false is true. Okay? So again, we just got that from our earlier statements. So now we're going to put that together and we're going to look at the values in the third column, P and Q. P implies Q, excuse me. And the value in the first column is P. We're looking for an and, so we want them both to be true. So this would be true because they're both true. The first column and the second column are true. Third column. The first column and the third column are false, so this would be false. False, true would be false. False, true would be false. Okay, now our last step, we want to look at the result from this column, which is our fourth column. Let's circle that in blue. And we want to look for the result of this column. And we're looking at an implied truth table, not an and or an or. So we're going back to what we did at the beginning. So true and true, so we have here true and true is true. False and false is true. False and true is true. Remember the order that we have to go in. And then false and false is true. So when we got to this the third one here, we have to remember that this part is stated first, and this part is stated second. And it makes a difference when we look at our truth table, when we have false as our antecedent and true as our consequent, then it makes a difference in terms of our result. So since all of the values in our chart are true, then we have a tautology, and so we have a valid argument. So the other thing that we bring up in this section are some different argument forms that we will be looking at. So what we just proved was the modus ponens, we just proved that with the chart above. And so what that is called, another name for that, is law of detachment. Okay. Another argument that we can use is modus tollens. And modus tollens, another name for that is law of contrapositive. Our third law is called disjunctive syllogism. And the last one is reason by transitivity. So if we look at this first one, we just proved this one. And this one was, we rewrote it as P implies Q and P implies Q. That was our first one. So if I wanted to rewrite the second modus tollens, I would have, and I'll do this one in red, P implies Q and not Q implies not P. So that's what we're doing when we are using these arguments. And I could prove each of these arguments using a truth table. And to prove that they're all valid, I would end up with a tautology when I did each of those truth tables. And I'll leave that to you to look at. They are in the book in this section, and you can go through and look at them if you had any questions about that. Okay, so here's some arguments, and we want to decide whether, what argument did we use for each of these different examples. So it says she studies or she talks on the phone. So she studies is going to be P, talks on the phone is Q, or is the symbol V. She's not studying. Well, studying we already decided was P. So not studying would be not P. She is talking on the phone. Talking on the phone we already decided was Q. So what we have here is P or Q, not P, therefore, the symbol I've got here with the 3 dots, therefore Q. So if we look at our choices for what we would have there, that's an example of the disjunctive reasoning or disjunctive syllogism. There we go. Okay. So let's look at another one and see if we can come up with the reason. If I study hard, then I will pass my test. Okay, so we're going to assign letters. Study hard is P. Passing my test is Q. So again, if I see anything in this next paragraph that talks about passing the test, then I will replace it with a Q. So here we have passing my test, so I call that Q. Pass the course, that's different. So we're going to call that a different letter. So we've used P and Q, so we're going to go ahead and go with the alphabet and say R. Well, here's passing the course again, so we call that R. I will be successful is a different statement, so we're going to call that S. I can use any letters I want. I'm using P and Q and R because typically those are the ones that we use for these logical laws, but you could use A, B, C, and D. It really doesn't make any difference. Okay, so now we know studying hard was a P, so we're talking about studying hard down here. Successful is an S, so we know that we have an S down here. So what we have is if we put all this together, we have P implies Q, Q implies R, R implies S, therefore P implies S. So you'll notice that basically we have conditional statements all the way through. So this is an example of a transitive reasoning. Okay, I hope that helps. Going. All right, so then we have some fallacies, and these are examples that tend to be common mistakes that are made that are going to come up with invalid conclusions. And again, if I went through and did the truth table for these, you would see that they are not a tautology, and so they do not come out to be a valid conclusion. So here's what we do. We want to determine whether or not this is an invalid or a valid or invalid statement. So we're going to go through and do our routine. Pat goes skiing, call that P. Amy stays home, we're going to call that Q. Amy does not stay home would be not Q. Cade will play video. Well, that's a new topic, right? So we're going to call that R. Cade will not play videos would be not R. Therefore, Pat does not go skiing. Okay, so that's our conclusion that we're trying to figure out. So Pat does not go skiing would be not Q. I'm sorry, excuse me, not P. All right, so let's put all this together. So we have, for Pat goes skiing, Amy stays home, we have PQ. That's our first part. Amy does not stay home, Cade will play the video, that's not Q and R. The next part's not an if, so we just write it as not R. Cade does not play video games. And the last part, therefore, Pat does not go skiing. So if we put all this together, we have P and Q, or we have P implies Q, and not Q implies R, and not R. Now all of that, if it's true, implies not P. So when you do a truth table for this problem, it gets very complicated and looks very confusing. You have to have a P column, a Q column, an R column. Well, we're dealing with not P's and not Q's and not R's also, so I have to have a not P, not Q, not R. Then I have to have a P implies Q column. And I'm going to run out of room there, but I'll keep going and try it. We're going to have a not Q implies R. Okay, so these are all our different columns so far. So right now we have one column for that, two columns, 3, 4, 5, 6, 7, 8. Now our next column is going to have to be basically everything probably on the left-hand side put together, and then we're going to put in our last column. Now what you've got here for our next slide is a very brief summary of all that. So instead of giving you all those columns, I'm just giving you the first 3 and the results. And you'll notice in the results that you have a false. And because you have a false, this is not a tautology. And so we've shown that this is not a valid conclusion. Okay, so here's our last one. And this is using information from Lewis Carroll, who is one of the author of Alice in Wonderland. And he's fairly well renowned for his logic problems. And so what we're going to do is we're going to look at some of the arguments that you might see in his books that are strange, and we're going to apply some of our logic knowledge to that. So we have this statement, babies are illogical. So basically what we're saying is that if you are a baby, then you are not logical. Okay, so logical is going to be the normal thing. So we have babies, and we're going to call those P's. Okay, and then we have logical. Okay, so somebody who is logical, and we're going to call those Q. Okay, the next sentence talks about nobody's despised, or people that are despised. So we're going to call that, we're going to say that people are despised. And we called that S. And then we talked about people who manage crocodiles. So we have crocodiles, and that's going to be our R value. So we're going to try and put that together. Babies are logical, or sorry, babies are illogical. Look at our next slide and show you that. Okay, so this is all we talked about just now. Okay, so here's what we have here. Babies are illogical. So remember, if we go back, that babies are P, logical is Q. So if we have illogical, that means not Q. So babies are illogical would be P implies not Q. Okay, going back, nobody is despised who can manage a crocodile. So managing a crocodile we called R. I'm going to erase this so we can see it better. Managing a crocodile we called R. And people who are despised are called S. So it says nobody is despised who can manage a crocodile. So basically we're saying if you can manage a crocodile, then you are not despised. So again, crocodiles are R. So if you can manage a crocodile, that would be R. Then you're not despised, not S. Okay, and the last part of the paragraph was illogical people are despised. So illogical people, again, was not Q, and despised was S. So then we have not Q implies S. So this is what we start with. Now we can rearrange the structure of these conditional statements, and we can switch these two statements. So when we do that, we end up with this order. So we have the P implies not Q implies S, and let's talk about this last part here. So then what we have for our last sentence here is R implies not S. So I want to go back and review something real quick. P implies Q is equivalent to its converse, not Q, oops, sorry, let's try that again, is equivalent to its converse, which is, it's contrapositive, which is not Q implies not P. So when we look at this statement, what I did with R implies not S is I switched them and I negated them. So if I switch them, I get not S implies R, and then negate them, you get R implies not S. I'm sorry, wrote it funny. S implies not R. So this statement, S implies not R, is equivalent to R implies not S. So what we did is we replaced that statement down here. Now the reason we're doing that is because if we can get the problem so that we have these common terms on the diagonals, is what I like to think of it, then we have a valid argument using the transitive situation. So that's what we've done here, is we've replaced it all and we've gotten this valid argument that P implies not R. So remember that P was talking about babies and R was talking about crocodiles. So P is if you are a baby, not R means then you cannot manage crocodiles. And that is a logical statement. That does make sense. So what we've done is we've used some of our properties. We've used the transitive property, we've used the contrapositive property, the equivalency properties to prove that this is a valid argument. So even though it did not appear valid or even realistic, it was a valid argument. All right, I hope this helps. We are getting ready for the test to come up soon. So start preparing for that and go through and get your materials for that done. I hope y'all have a great week, and I will talk to you soon.